Oh. You guys, this was just too interesting to pass up on this set. Oh, so you want those. So you guys, check out what's happening. In this picture, I start off with a triangle. Equilateral triangle, each side has length 1, and I want to take each and every one of these 3 sides and cut into thirds. Now for the middle third here, if you don't mind, I'm going to project 2 more sides to create another equilateral triangle. It's just that now the length of these 3 sides is going to be 1/3. And I'm going to do that for all 3 sides. And here's the corresponding image I created. Now I want you to take each and every one of these line segments here, each one of them, and I want you to subdivide in 3 parts and protrude another equilateral triangle whose sides are going to be 1/3 the length of that line segment I just protruded from. And repeat that process indefinitely. You get images that kind of look like this, stopping at maybe the 3rd stage. Now, from here to here, did your perimeter increase?
No.
From here to here?
Yes.
I think it did. Therefore, from here to here, it should
increase again.
increase. From here to here, it should increase. So what do you think was going to happen if I repeat this process indefinitely? What's going to happen to the perimeter of this geometric figure?
It's going to increase indefinitely. Create a black hole.
It's like a black hole. You know, in a sense, I see your point. I think what's going to happen is that the perimeter is going to increase without bound. However, if you look at the area from here to here, yes or no, does it increase? Yeah. Does it increase again?
Yep.
Do you think the area is going to increase without bound?
Yes.
The area?
Yeah. No.
I think the area is increasing, but according to my geometric figure, I mean, it's a finite bounded region. I think the area is going to remain finite, but the perimeter increases without bound. And so it sounds like there's some kind of contradiction here, because the perimeter does increase without bound, but the area remains fixed. This is kind of like the foundations of fractal geometry. Yeah, and it's a big deal, particularly nowadays when it comes to satellite imagery. Satellite imagery exploits really what's going on here with this picture. I think there's self-replication. I think if I zoomed in here and blew up, I get a piece of one of these graphs. I think the more and more I zoom in, especially way out of this particular sequence, I get a previous image, or at least a portion of it. There's self-replication in terms of scale changes. It's the foundations of fractal geometry, and the author wasn't asking anything specific in terms of numbers, just what's going on with these limits. That's really what it's asking. Sir?
Is it the same kind of idea how when you have like a curve going closer and closer to a line, you can have finite area, but
Very much, very similar to that. I agree completely.
Is it the same thing too as like square, and then you cut it in half, and then you cut it in half, and you
No.
cut it in half, where the area remains? We know the area of the square, but we cut it in half.
I think this is what you're thinking of. And can I use triangle instead because it's easier? I think this is what you're thinking, and I personally think this might be a better example. But watch this. I'll start off with, yet again, an equilateral triangle. Whoops. How about if I start with what you can see? So let me start off with an equilateral triangle. And it's got a fixed area. It's got a fixed perimeter. Done. And let me shade it in. But if I took the triangle and removed from it another equilateral triangle by connecting midpoints, now let's look at what's shaded in. Because I removed that middle inverted triangle. Tell me from here to here, what's happened to the area?
Decrease.
Decreased. What happened to the perimeter?
Increase.
It increased. Now let me do it again. Let me take those 3 equilateral triangles and remove another equilateral triangle from within. I think I get something that kind of looks like this. You guys keep talking. Area has decreased, but perimeter has increased. And if I repeat the process over and over again, the area is going to go to what? 0, but the perimeter is going to go to infinity. I think this is even more extreme, and maybe this is what you're thinking of a square, but you have to rotate one of them at the first stage of the game.
No, that was kind of something else, but that's okay,
Oh,
but this is a
maybe
good,
not.
this is a good example anyway, yeah.
And in fact, it's so famous, it's called the Sierpinski triangle. Yeah. Again, foundations of fractal geometry. Seems to have contradictions, but really interesting stuff. Give me the name of a famous 20th century artist who didn't realize he dove into all this until he started hearing professors speak about it in classes. Later.
I know Alex Gray does a bunch of this stuff, but he's probably more modern.
Yeah,
Alex
sounds
Gray.
so familiar.
It's the guy with like the hand drawing the other.
Yeah, he does all the
Yeah,
tool.
M.C. Escher.
Yeah.
He illustrates
M.C. Escher.
this idea of going to infinity at the outer part of some of his diagrams. Yeah.
He's the one that
Also
does the
tessellation.
staircases, right? The infinite staircases.
Yeah, which seemingly has
Yeah.
multiple universes that don't interact.
It's above Tabitha's desk, so.
Oh, and I've got a few really nice framed ones in my office. Yeah. All right, I'll stop talking. Did I address that okay, everybody? Nothing more in depth than that.
Well, it wants an answer, right?
Does he? Let Elsa be the perimeter of Ln. Brian, excuse me, I messed up my letters. Who cares? Show this limit goes to infinity. I just think you need to talk.
Oh, for B, that's my question.
Then for B, oh, he wants you to find it.
The answer is 2 root 3 over 5 to that.
Well, what would be the area of the first geometric figure?
1/2 base times height.
So 1/2 times.
Is that
Times root 3 over 2.
So times root 3 over 2. I agree. You guys okay with that? Be honest.
root 3 over 2? Is that what you just said?
1/2 times root 3 over 2. Do you guys agree?
Oh, okay.
Everybody?
Mhm.
Okay, because I'll talk more if you want.
Is that because it's equilateral?
I don't know. Depends how you come up with the number. You could say, since I'm equilateral, when I drop an altitude from this vertex to the other side, making a right angle, the length of that altitude is going to be root 3 over 2. And now I got 1/2 base times height. There's my number. Maybe you didn't use the idea of an equilateral triangle. Maybe you simply used the idea that one of these angles has to measure 60 degrees. And you said the area of a triangle could be interpreted as 1/2 times the product of two sides times the sine of the included angle. You get the same darn thing. Or maybe you gave up and didn't use any angles. Without using angles, how would you compute the area of the triangle?
Oh, we went over this. I do remember.
Did we?
Yes.
Go ahead.
4 different ways to carry this.
Heron's formula. Heron's formula.
Thing.
Do you remember Heron's formula? So many blank stares. Area can be computed by looking at the square root of the semi-perimeter times the semi-perimeter minus one of the sides times the semi-perimeter minus the second one of the sides times the semi-perimeter minus the third side. It's a nifty way to compute the area of a triangle without knowing any of the interior angles. Or the interior.
It's also
outlook.
a formula.
What's that?
It's also a formula for it.
Does that thing write it the same way I do?
S squared.
Oh, actually, that comes from what I was doing before, as opposed to Aaron's formula. Oh, so what's the area of the next one? It's just the same thing, isn't it? Oh, you're right. I made a mistake, darn it. I guess it's the area that I had before. I'm just adding the area of 3 of these triangles. But to add the area of 3 of those triangles, what does that really mean I'm adding?
Triangles with
All right, I got an idea. How about adding?
You're adding 3/4 of that.
Where'd you get 3/4?
Oh, no, never mind.
Well, aren't the sides 1/3?
I being too sloppy, you guys? If I'm not being too sloppy. Seems to me the area of the original was 1, 2, 3, 4, 5, 6, 7, 8, and 9 of these things. But I'm adding a third of them. So I think what I'm adding is a third of what the previous area was. And I think the next area value, ace of 3, will be all this stuff. Can I call this pound symbol? It's just pound symbol plus 1/3. I can't write 1/3, sorry. Times pound symbol. Oh shoot, you guys, this looks like a sequence that's geometric. And so when I look to corresponding sum, that'll be a geometric series. And if I compute the sum of geometric series, wouldn't that just simply be my A over 1 minus R? Or shall I say, this A over my 1 minus R? Or shall I say, I don't know what I should say. Help me with this.
Multiply by 3.
Ay, 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 I'm too tired. Does that give me 3 root 3 over... I can't do it today. Is that an 8? Assuming I'm correct with my arithmetic.
That's the final answer.
Yeah, what does the book say?
I think it said 2 root 5. 2 root 3 over 5.
2 root 3 over 5?
It wasn't that, I'm pretty sure.
Oh, did I make a mistake with my arithmetic?
Yeah, 2 root 3 over 5.
Did he go out to infinity?
Yes.
I don't know, you guys had a miscount. Because I think I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 of those triangles, but I added 3 more. That means I had a third of them.
Only computed it for 5, 6, 1.
What's that?
She only just computed it for us.
This is what the work he did right here.
Yeah, show me. He came with a different R value. So he says start off with a root 3 over 4. We got that as our first value, but add to that the area of the 1, 2, 3 triangles.
I would think the height would be different, would it not?
You know, I wasn't even looking. I was trying to avoid the whole issue of computing areas of triangles. I was just suggesting that from here to here, this triangle in here is simply going to be an equilateral triangle with 1/3 the length of the size of before.
I see.
That's all I was doing. I'm sorry, I'm just checking if I counted correctly. I counted the 9. And that's the original one I had. I don't know, I don't see it. I can't see that it did anything wrong.
It's supposed to be the area of like 7.
I know, I was just going on one step. I'm just saying each subsequent step's going to duplicate the same process. I don't see it. I'll have to think about it.
Would it be 1/3 pound symbol or 1/3 of the new triangle?
1/3 of the total previous area. 1/3 of the ace of 1. Get you, Sean?
Don't you, on the next one and the ones after, don't you lose a triangle? Each of the equilateral triangles only have 2 of them that are added to them?
Oh, so you're saying maybe in the process what I gained or lost over here is different than the subsequent steps.
Yeah.
Oh, I wasn't going that far. I was just looking at the first step. Can I count real quick? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You know, that might be true. You know, that really might be true. As a matter of fact, with my black pen, let me show you what's really being added. That triangle, this one, this one, this one. Sorry if I'm being a little sloppy, but I think I got a total of 12 of them I'm being added? You know, maybe you're right. Maybe the subsequent step down here, I've really got a different factor here. I'd have to count that. I want to compute areas. I'd probably go in there and subdivide this into more smaller triangles, and if it's a different quantity, then I've got a different question mark number here than 1/3. And then maybe, if that were the case, I come in and say the total area is going to be my a sub 1 value plus whatever I get from this geometric series. Then I'd be looking at my new a value over my 1 minus r. And a, of course, would be this quantity here. It's just that my r might be different, but I'd have to go and count. Do you mind if I don't take time in class to do that? So I didn't realize he wanted a specific value. And just so that I don't get behind, I took some time, if you guys don't mind, if that's okay with the homework, maybe just pace things up a little bit. I took the liberty to give you some examples.
Too big.
Are you gonna post solution to those?
No, I wanted to go over these in class.
Oh, okay.
Do them together today.
Sounds great.
Gotta zoom out a little.
Zoom out.
Yeah.
See if I can keep up with this.
So you guys, I think with the tools we have, we're fairly limited in that, as of today, I can only determine if I have convergence for a geometric series if it's you guys tell me. Geometric. And if it's geometric, then I think the series is going to be this number. And I maintain, whoops, that's not his notation, hold on. He likes this instead. And I maintain with this geometric series, it's going to converge if R and absolute values is between -1 and 1 for R, but R and absolute values is less than 1. I do think, however, if R in absolute values is between 1 and -1, this infinite geometric series converges to,
0.
well, more specifically, if it's infinite. If it's finite, I know the formulas will look different. I'm going to focus on infinite series. I do think there's another type of series, however, that you and I can evaluate the sum for, namely a telescoping series. Let's talk about something else. It's a theorem. Let's just, you and I suppose, that I've got a series that converges. I maintain that if a series converges, it's got to be the case that when I take a peek at the limit of the nth term, I then increase that bound. It's got to be this. It has to be. To show you why, you and I go back to our definition of convergence, and here's the key to everything. So tell me what the definition is of convergence for a series, not a sequence. What does it mean to say that a series converges?
It holds in on a number. Or yes, specific.
Kind of narrows in at a specific number.
Okay, but that's not a concrete, rigorous definition, though. What's our rigorous definition of convergence for an infinite series? That is a 0.
Obviously don't have.
Yeah, apparently not. Series converges, I misspoke. An infinite series converges if the corresponding sequence of partial sums converges. But now that I'm talking about sequences of partial sums, a sequence converges simply if the limit of the nth term of the sequence goes to some fixed finite real number. So that's what it means to converge for an infinite series, geometric or otherwise. Notice, by the way, I'm being so abstract. I never indicated this is a geometric series. It could be any series. So let me prove to you this has to be true. So proof. Here's what S of n is. The nth term of the sequence of partial sums is just this, isn't it? Yes, sir.
I'm still confused on how a sequence of partial sums differs from a series.
Hugely. Let me illustrate it. Take a peek at this piece right here. You guys, I know I'm being a little silly, but where do I stop? I don't. So let me change the name of the game. Let's take a peek at something like, how about just a sub 1? Or how about a sub 1 plus a sub 2, the sum of the first two terms? Or how about the sum of the first three terms? Now, from these smaller sums, I'm going to build a whole new sequence, not a series. I'm going to build a whole new sequence of numbers. The first one I'll call S of 1. The second one I'm going to call S of 2. The third one I'm going to call S of 3. You guys, let's keep going with this. Let's go down to, how about S of K, which is A1 plus A2, all the way down to stop at A sub K. Now, I think I've just built a whole new sequence of numbers, S1 through Sk, and that's going to be my corresponding sequence of partial sums from the original infinite series. So, here's the original infinite series, and I think here's the corresponding sequence of partial sums. Notice it's a sequence. Now, I confess, I can carry this out further as an infinite series, but as an infinite series, I take that back, I'm sorry. I can build this out to an infinite sequence. But as an infinite sequence, it's only going to converge to the limit of the kth term. That k increase that bound is going to go to some fixed real number. I'll call it L. I don't care what it is. But this way I can just talk about a finite sequence of partial sums and then take the limit as the kth term goes to infinity.
So are you saying the sequence, so with the sequence S, S infinity equal an in this example that you did?
I hate to talk about S sub infinity because I always want that subscript to represent the value for the index variable. It doesn't technically equal infinity exactly because infinity is not an integer. It's not even a real number.
Okay, so with the sequence carried out to infinity equal
That's better. Equal the L.
Equal the sum of an from 1 to infinity.
Yes, if the kth term of the sequence of partial sums goes to L, that means literally this infinite series evaluates that number positive L. That is to value that infinite series. I agree completely. So everybody, let's come over here. Maybe it's not an infinite series. Now I just got the nth term of the sequence of partial sums. I stopped at a sub n. Do you think I can rewrite it this way? Shoot, what would the name of that be? Gosh darn, it would be
L.
S sub that last one. I heard that. Plus my a sub n. Or shall I say a sub n can be interpreted as S sub n minus S sub n minus 1. It's just that, you guys, if I allow n to increase that bound, what can you say about this? Remember, I'm assuming the infinite series converges. What'd you, oh sorry, is it really 0? You meant
L.
L. What do you think you say about this piece right here as n increase that bound?
L minus S.
See, I think it's just L. Because I think as n increase that bound, both these terms of the sequence of partial sums are going the same darn limiting value. It's just L. It's just L minus L is. Oh shoot, I just proved what I want to show. This is not ground shattering in this form. This is not going to help you that much because, to be honest with you, I'm assuming I got convergence of a series, and you and I want to have some tests to determine whether the series converged or not. The significance about this theorem is the following. And this is the problem with the way we're teaching the math courses at this level. We don't have a prerequisite of basic logic. Because I think when it comes to this theorem, this is a mathematical statement of the form. If P, then Q. I call it a conditional statement. But whenever a conditional statement is true, is contrapositive is true as well. Meaning I get to interchange premises and conclusions and negate them. You guys, I'm not going to embarrass you with the question. How many of you have taken a basic symbolic logic course? 1, 2, just 3 of us. It's 4 of us. So
Do they
I'm just
actually
simply saying,
teach symbolic logic here?
Yeah.
They do?
we teach an introduction.
Oh, what's that? The philosophy critical thinking?
Did you really?
Phil 4? Phil
I
12,
don't think I even
symbolic
know
logic.
such a course at university.
Yeah,
Gotcha,
get
but
that
you know, that's
next
typically put
semester
in some kind
maybe,
of
if I
discrete
can get into
structure
it.
course in a computer science department. That's interesting.
Yeah, I was talking discrete math, we did a whole section on the truth tables. And
Oh my gosh, yes, when I teach discrete mathematics here at Sierra, I dive very heavily into all my, yes. We're just in the middle of a budget crisis, they killed it.
I got the petition.
What's that?
I got the petition.
Do you really?
Yeah.
Yeah.
I just hope I filled it out, or wrote it right. Had to use Wikipedia a little bit
That's great.
for the course description.
Oh, did you really?
Yeah.
Oh yeah, I guess I don't have the syllabus on there anymore.
Nope.
You know, you can go on the math webpage,
Huh?
the math website,
Yeah.
and you can go into select courses, or course descriptions, and the Math 15 will be completely described for you if you want to take a peek at it.
Okay.
In fact, when I do course descriptions of my syllabi, I just go in there and cut and paste to be legal.
All right.
To make sure I'm getting the right description.
Is this good for a petition though, or should I
That's
change
great
it?
to me.
All
That's
right.
great. So you guys, for the rest of us, I'm sorry if I'm waving my hands, but for a conditional statement, P implies Q, its contrapositive is also going to be true. It's got equal truth values. The original conditional statement. So I got a whole new theorem. And a whole new theorem is for free. I'm just going to list a contrapositive. Actually, I won't. I'll bring it up on the screen. It's that important. It's so important, I'm going to give it a name. If you guys allow me to come in and actually I can't start it. Go back to my page. I should have done that. Yeah, I know, I should have done that. I guess at that point down below, I didn't see that fast. It's one of my very first tests. So official, I'll give it a name. I'll call it my test for divergence. And when it comes to my test for divergence, it's simply the contrapositive statement. It simply says if the series diverges, it's going to happen only if the limit of the nth term does not go to 0. That sounded clunky. Can I rephrase that? Got a series? If the nth term does not go to 0, your series diverges. So that's our first real test.
That.
It's the contrapositive this. It's interchanging premise and conclusion and negating them.
And this,
Because the word if is in front of this phrase.
this sheet is on your website.
Oh, it's been there for well over a week. Just go to the in-class materials. Now, you guys, I do think I have some other tests to look at. For example, check this out. Special series, geometric. We discussed it. And I confess, you guys, when I typed this up, I wasn't looking at your author text. And so notice how he typically starts at an n value of 0. I started at 1. It looks a little different. But in the end, you get the same a value, the same y value. Oh, there's another one in here that's kind of interesting. Test for divergence. So the test for divergence says the following. Sorry, I said test for divergence. I meant take a look at the integral test. It says I've got a series, and if it matches up to a function f for which that function is continuous, positive, and decreasing, it's necessarily the case that if the corresponding improper integral converges, then so does my infinite series. As well as saying that if my improper integral diverges, then so does the corresponding infinite series. This is so important. Can I take a peek at it real quick? It is time for some pretty pictures. Oh, that's not going to be very pretty.
This only applies to integral
Give us a
functions,
little
though,
pretty, though. I'm sorry, did you say something?
right? It only applies to integrable functions, though. You can't use it on, like, say, e to the negative x squared.
Well, I guess it doesn't do you much good unless you've got an integral function, you're right. So everybody, let's take a quick peek. N-axis. Y-axis. Let me draw you guys a function. It's continuous, positive, and decreasing, at least for values of x, or in this case n, at as big as 1. And on my horizontal axis, let me talk about some values. So, what was that?
No, I was just saying, this is why I hit pause.
Would you guys agree with this? Using pretty colors. Since the horizontal width of each of the subintervals is 1, can't they think of the area of the very first rectangle as nothing more than base of 2? After all, my function, f, coincides with the nth term of my series for values of x that are just restricted for the positive integers. And I maintain I could talk about the area of these particular rectangles, not triangles. I don't want you to get, do you mind if can I use my hands, clumsy hands? Can I take those blue rectangles and slide them to the left 1 unit? If I slide them to the left 1 unit, I think my picture looks a little bit different. I think it looks like this. Do you guys agree? And if that's what a picture looks like, wouldn't you think I can make some kind of comparison like this? Namely that when it comes to the sum of the a sub i's, you guys, I have no idea what they are. I gotta look at the picture. I don't have any memorized. I'm just talking naturally. How about a sub I is I range from 2 up to n? You guys, isn't that the same thing as the area underneath this curve from here to here?
If I starts at 2, then wouldn't it be from 2 to n?
Yeah, that's what I'm saying. I range from 2 to n.
But you've got from 1 to n.
No, wait, stop. Yes or no? Is the sum on the left-hand side an equal sign to the sum of the areas of these blue rectangles in the second picture? But I think it's A2 plus A3 all the way up to AN. I'm missing a few on the screen, I admit. You guys, this is too important. I gotta stop. Thank you. I think I made a mistake. I think when it comes to this relationship, I think the sum of those rectangles in blue in my second picture is actually a value that's not as big as the area underneath my curve as x ranges from 1 to n. And so I think, technically speaking, there's an inequality here. Do you guys agree? Shoot, maybe I should be labeling this x, not n. My apologies. Because I think there's a discrepancy between the sum of the area of the rectangles in blue and the actual area underneath the curve. By the way, this function only has positive values strictly to the right of n, and so I think, I don't know, maybe I shouldn't think. What do you think? Is that okay?
So are we comparing these two graphs where
No, I'm doing this. Here's what I'm really doing. I'm comparing the second graph with the following. So my question really is this. Here's the sum of the areas of those blue rectangles in the picture down below. But I think this represents the actual area underneath the curve as x ranges from 1 to n. Don't you guys agree that this area in blue, the sum of the areas of this rectangle, is less than the area underneath the curve? Because I got all this discrepancy here, and here, and here. That's what I'm suggesting. By the way, does equality hold here? No, I don't think it does. Remember, f is positive. My sequence is positive terms. My function f is strictly positive. I think there's an inequality here. Do you guys agree? So help me with this. Because my function is always positive, if I call this thing right here the nth term of the sequence of partial sums. Yes, David?
And I'm sorry, why are we shifting them?
Yeah.
Well, what's the point?
Just so you can see a relationship between the area of these rectangles and everything up to n. See, I went beyond n with the first picture.
Well, why isn't it a sub n minus 1? Good, because you're going back one?
Yeah, because I took each and every one of these rectangles and shifted it 1 unit to the left.
Okay.
And I think now my a sub n is below the curve, not like this, above it. Not above it. Are you there? All right, because here I go. Yes.
So the integral from 1 to infinity is the exact area
Underneath the curve from 1 all the way out, not just stopping at n.
Okay.
And I maintain, you guys, when it comes to the sequence of partial sums, because f is strictly positive, this sequence is increasing. However, if I make the assumption that the corresponding improper interval converges to something like, I don't know, some number big M, shoot, now I got a sequence of partial sums. That's strictly increasing, that's monotonic, and bounded above. That being the case with the theorem I proved last time in class, that means I get to exploit the monotonic bounded sequence theorem, and now proclaim that this particular corresponding infinite series is going to converge as well. I've just proved the first part of the integral test. Now I think to prove the second part of the integral test is just as easy. Here's my function. Well, let me modify my picture a little bit. I meant to say, here's my function. I maintain, using maybe a different color like red, the area of this rectangle can be represented by the first term of the sequence. It's a sequence, the first term of the series. I think a sub 2 could be represented by the area of this rectangle, all the way up to maybe this rectangle right here, which is nothing more than a sub n minus 1. So you guys humor me with this. What do you think you could possibly say about the relationship between this particular sum, as I range from 1 to, help me with this, is it n minus 1? I'm not looking. My glasses are off. And take a peek at this relationship. Do you agree? Oh yeah, I messed up, didn't I? Actually, when you sum together the area of those red rectangles, I guess the relationship